Machephy Eduworld.
So just recapitulate everything first, then go ahead. So first thing we learned here is that current carrying loop acts as magnetic. Current carrying loop acts as magnetic dipole. Acts as magnetic dipole. And magnetic moment of that loop, for that magnetic moment, we defined it as m vector equals to n I a vector, where a is the area, n is the number of turns, I is the current. So for a circular loop, we know that magnetic field B is equal to mu naught I by 2 pi r. There is a current carrying loop of radius r, and current is I. From here, I can write current is equal to 2 pi r B by mu naught. For this loop, if you want to write the magnetic dipole moment, so just leave out this n. So value of current, I will put it as 2 pi r. This is m vector equals to IA vector. This becomes equal to, if I put the value of I here, that will be 2 pi RB by mu naught, and area is pi r square. So just leave out the vectors now. If I want to write the magnetic field, so that will come out to be 2 pi squared like something. Pi d by r. Just do that. You know, I by 2r. So this will be 2r. This will be 2r. So magnetic field will be mu naught 2 pi r cube d by mu naught. इसको इधर ले गए तो mu naught by 2 pi into m upon r cube. इसको हम कंपेयर करना चाहते हैं इस वाले फॉर्मूले से. इलेक्ट्रिक फील्ड इज 1 by 4 pi epsilon naught into kp upon r cube, kp upon r cube, like this. So compare it with this. I will write it here. यहाँ पे mu naught by 4 pi into 2m upon r cube. So if I write 2p upon r cube, that is magnetic field on the axis of the dipole. So this acts like, this is the magnetic field on the axis of dipole, on the equatorial side. On the axial line, the equatorial line. So there's a similarity between these formula. So this position is also called the end-on position. So this proves that a circular loop acts as a magnetic type because of the analogy. Note this down. So direction of the magnetic dipole and magnetic field is the same. So we can we can consider all of these loops as the as a dipole with the magnetic field in the same direction as the dipole. And this is the reason that hydrogen atom and many atoms, they act as little dipoles. They act as little dipoles. And in the chapter magnetism and matter, we'll understand how these little dipoles, they can add up their magnetic field to generate permanent magnets. Very interesting phenomenon. So magnets were one of the things that Einstein found very interesting, very interesting, because he was surprised. His dad gave him gave him a magnet, a pair of magnets, and he was surprised that two magnets can attract each other without even touching. And on a completely different note, I'll tell you this in this class, but okay, it's out of your syllabus. But magnetic field is just electric field in relative motion. That's why they have a very common and similar properties. Einstein was the one who worked on relativity, was the first to propose relativity, both special relativity and general relativity. We'll be discussing a bit of that in modern physics. थोड़ा सा ये syllabus तो उतना ही पढ़ेंगे. And I'll be telling you modern physics और बहुत सारी अच्छी stories. The development of this electromagnetism बहुत ही chaotic था. There's बहुत सारे scientists थे, some mathematicians, the experimental physicists, and Indian Maxwell. He just wrote four formulas, और उसी पे using that four formulas, half of the portion of physics, your physics book is covered, starting from electrostatics to electromagnetic waves. Just those four formulas. And electromagnetism is one of the most complete theory. कोई भी exception नहीं है इसमें, कोई भी limitation नहीं है इस theory. Electromagnetism is one of the most complete theory. Newton's law के limitations हैं, but electromagnetism के कोई भी limitation नहीं है, कोई भी drawback नहीं है. It's a perfect theory, and that is why अगर experimental results से दो theories verify हो रही हैं, मतलब एक if you can you have a debate कि electromagnetism गलत है या फिर दूसरी कोई theory that you put on वो गलत है. So electromagnetism always is right, is always right. So one of the thing about magnetic field and electric field is that they travel at the speed of light. है ना, बस just switch on किया electric field तो बहुत थोड़े time बाद there will be electric field in the region. and that is the amount of time that takes light to travel that distance. So electric field and magnetic field, they travel at the speed of light. ऐसा नहीं कि स्विच ऑन किया और तुरंत कहीं हर जगह पहुंच गया. It travels at the speed of light. Okay, moving on to next thing that is important to us. So we have to prove here the magnetic field. Every loop can act as a magnetic field, but we can also consider small dipoles or small bar magnets. Calculate magnetic field due to that. A small bar magnet. I'm not talking a big bar magnet because a big bar magnet is made up of very small magnets. So small bar magnet like this, it has two poles, south, north. We can take north as plus M and south as minus M. From the center, on the equatorial side, that is called the end-on side, I have a point P where I want to calculate the magnetic field, P vector. This is the center, and the distance between the center and this side is L by 2, or is take it as L, and this can be taken as M. This is very analogous to the electric dipole. I'm not going to go into much detail here. You already know the values of magnetic field. It's called the end-on position or equatorial position. To calculate accurately, let us say the distance of point P from the center O is R. The value of magnetic field that comes as mu0 by 4 pi 2 m r whole divided by r square minus l square. जैसे इलेक्ट्रिक फील्ड के लिए डिराइव किया था वैसे ये भी आएगा. This is Newton per ampere meter. That is Tesla. And the direction of magnetic field is along the direction of the magnetic moment. If r is much greater than l, you can write this as B vector is mu0 by 4 pi into 2m upon r cube, 2m vector upon r cube. That is 2 kp upon r cube, where k is mu0 by 4 pi. And similarly, we can derive the magnetic dipole moment for the broad side on. That is, if my point is on the axial line. The point is on the axial line, and from the center, this distance is r. So magnetic field will be towards the left direction. This is called the broadside on position or the axial position. And here, if you remember, we take the magnetic field from plus m will be away, from minus m will be towards, then cos theta projection length, then 2b cos theta aa jata hai. And then we do some calculation, just like we did in electric field. Let's just write the result directly. So mu0 by 4 pi m by r square plus l square to the power 3 by 2. If you want to write m vector here, see, the m vector is along from minus m to plus m. M vector is from minus m to plus m. Okay. So m vector is from minus m to plus m. So direction of magnetic field is parallel in this case, but here direction of magnetic field is anti-parallel to the M vector. So I'll put a negative sign here. Newton per ampere meter, that is the SI unit. And if R is much greater than L, B vector will be just minus mu naught by 4 pi M vector upon R cube for the axial position.
Sir, in first case, how in the last formula it became R cube?
There will be a square here. So R square minus L square will become R to the power 4, and R to the power 4 will cancel. Now moving on to the next topic. So we already know that torque on a current carrying loop is M cross B, that is M sine theta. And from here we can calculate the potential energy of a magnet in a magnet. Just like we did it for potential energy of an electrotechnique. So potential energy of a magnet. What is a magnet? A magnet is a magnetic dipole. Potential energy of a magnetic dipole in magnetic in uniform magnetic field we calculate. So suppose initially you have a magnetic field in this direction and loop was like this. Loop was making angle theta 1 initially, and you have rotated it now. Now the angle that is made is theta 2. So we can write the torque is equal to mp sine theta. What is the work done? Work done in rotating is tau d theta. To calculate the total work done, we can integrate this. When theta varies from theta 1 to theta 2, this will give you the total work done. Tau is mb sine theta. Integration of sine theta is minus cos theta. So this will be minus mb cos theta, upper limit minus lower limit. That is work done. This is this is the work done by external agent. Means you have to do this much of work to rotate it in this direction. So that will be mb cos theta 2 minus mb cos theta 1. Now work done by external agent is stored as potential energy. Work done by external agent is stored as potential energy. Stored as potential energy. Okay. The given condition is that change in kinetic energy should be 0. So W will be equal to U. U is equal to delta U, change in potential energy. So that is minus mb cos theta 2. This is W. So delta U is final potential minus initial potential. That is minus mb cos theta 2 minus mb cos theta 1. So I can write potential energy is minus mb cos theta, where theta is the angle between the axis of the dipole to the magnetic field. And finally, we can write the potential energy of a magnetic dipole is minus m dot, if I want to write it vector form. That's the result that we are already using. Okay, now a few things I'll be giving you as homework because we have already studied electric field, so I don't think I need to uh, go through those things again. So first thing I'll be giving you is giving you some questions. First is what are magnetic field lines? You can just refer your book and write down the answers for this in your notebook. Just write a proper definition from your book. Then second question will be write properties of magnetic field lines. And in exam, when you write properties of magnetic field lines, you must also draw a diagram along with the property. Write properties of magnetic field line. Okay, so at least 5-6 properties you have to write. ऐसे नहीं 2-3 property लिख दिया and that is all. 5-6 properties, write it down and also with the along with the diagram. Along with the diagram. Another homework I'll give you as okay, this question it's a good question, but it will require a little bit of mathematics, but I think you can do it. Show mathematically that bar magnet and current carrying solenoid are equivalent. Current carrying solenoid are equivalent. So of course, you can draw a magnetic field line and just show it, but you have to show it mathematically. Prove it using integration. You know the magnetic field for a bar magnet. You know the magnetic field for a current carrying solenoid. And make some assumptions and try to complete it. And you have to submit it on the group by today evening. Submit all these questions by today evening on the group. Okay, next we're going to start with the Earth's magnetic field. So Earth has a magnetic field of its own. The reason is what is people think about the reason. They scientists give the reason, but we are not sure if those are the reasons. But we know that there is a magnetic field around the Earth, and we know its behavior. And this magnetic field has helped the navigators in the early 1600s to navigate and go all around the Earth. So we're going to observe this magnetic field. Okay, so first thing we have is this the magnetic field arrangement of magnetic field lines is like this. It starts from the South Pole and ends at the North Pole. That is the geographical North Pole. Okay. So axis of rotation is something like this. The Earth rotates about this axis. The Earth rotates about this axis. So the axis about which Earth rotates is a bit different. This is axis of rotation. And axis of rotation, this direction is the Antarctica. And this is called the geographical North Pole. Okay. So this point is called geographical North. Geographical North. And did I say Antarctica? No, this is the Arctic. This is the Arctic. This is the Antarctic. And here we have the geographical south. And our magnetism, it has an axis of its own. It has an axis of its own, and this is called, on geographic south, we have the magnetic south pole. This is the magnetic south pole, and magnetic south pole, I should call it geomagnetic south pole. Geomagnetic south pole. Yeah, southern magnetic pole, northern magnetic pole. Okay, so this is the northern magnetic pole, and this is the magnetic south pole. This is the magnetic north pole, and it appears as the magnetic field starts from the north pole, that is magnetic south pole, and terminate at the magnetic north pole. So naming might be a little bit confusing, but this is how it is. So if you see, there is a if you put a compass, then the compass will become parallel to the Earth's surface at the equator. Magnetic field is parallel to the Earth's surface near the equator. But here there is a little bit tilt towards the Earth. Means it makes some angle with the horizon. And at the poles, the needle points vertically downwards. Whereas with the horizontal, it makes an angle 90 degrees. So this is something called a tilt. This is called a tilt. Means we can draw a horizontal line, and we can put a compass here, magnetic compass here, and this angle is called a tilt, angle of tilt. You can take a screenshot of this and maybe draw the diagram later. We'll move on to the theoretical aspect of it. So basically, we have these two angles. I've written this as delta, and I'll write this angle as T. We see the same thing in this diagram. This is geographic North Pole. Earth is rotating about North Pole. About the geographical axis, this is the northern magnetic pole, this is southern magnetic pole. And if you want to draw the magnetic field line, you can assume that on the northern magnetic pole, there is a south pole of a bar magnet. So Mn means magnetic north, Ms means magnetic south. Just like we have a geographical equator, we also have a magnetic equator. Just like geographic equator, which is perpendicular to the geographical axis, we have a magnetic equator which is perpendicular to the magnetic axis. So write down some definitions. So first is geomagnetic poles. Geomagnetic poles. They will be defined like this. The two places where the needle, where the compass needle. So I think you know about the compass needle. It looks like this. There is a compass magnetic material which is kept on a pin, and one of the side is coated or painted red. The painted red part shows the north, and the side which is not painted or painted blue shows the south. This is called the compass, and this is the thing inside it. It's called the magnetic needle. Magnetic needle. So whenever you see this, the red, pointer shows the direction of the north. So to define geomagnetic force, these are the two places where the compass needle becomes perpendicular to Earth's surface. Becomes perpendicular to Earth's surface. So if you put a needle here, the compass needle will point out like this. The red will show away. The red will show away. And on this side, not here, but here. And on the northern magnetic pole, it will be showing towards the magnetic. So where the compass needle becomes perpendicular, those are the points, those are the places on Earth which are called geomagnetic poles. Then next is the magnetic axis of Earth. This is the line joining. The line joining the magnetic north and magnetic south. Next is the magnetic equator. Magnetic equator is a circle which is perpendicular to the magnetic axis of the Earth. These are the definitions that you should know. Then you have two angles. First is the angle of declination. This is angle of dip or magnetic declination, and this is just angle of declination. So angle of declination is the acute angle between the magnetic field line of the Earth at any point, that is the magnetic meridian, to the geographical meridian. So in this diagram, see the geographical meridian, it is like this. just like this. You must have seen those lines on the globe. Those are geographical meridian. So the angle that the magnetic meridian makes with the geographical meridian, that is the angle of declination. That is the angle of declination. Here, if we talk about the axis at the equator, this will become the angle of declination. Okay, but this is only at the equator. So angle of declination is the angle between geographic meridian and the magnetic meridian. So suppose at this point, this is the geographical meridian and the direction of magnetic field is along this line. So this becomes angle theta or angle D. And next is the angle of dip or magnetic declination. So this is like this. If this is the surface of the earth and the magnetic field line, let us say it is going like this. So this is the magnetic earth surface. And this is the magnetic field line, Earth's magnetic field line. So angle made by these two, angle made by the horizontal to the Earth's surface and this magnetic field. This is the angle of dip. This is angle of dip. So this is not called magnetic declination, but magnetic inclination. Sometimes, mostly the common term is angle of dip, but sometimes it's called magnetic inclination. So the Earth's magnetism is not parallel to the Earth's surface, it makes some angle with the horizontal. So the angle that it makes with the horizontal is called angle of dip, and angle of declination is the angle between the magnetic field line of the Earth to the geographical meridian. Geographical meridian are the lines that are drawn on the globe from pole to pole.